But let's shift track here a little bit to talk about a technology that has already changed a lot of things and is highly innovative, extremely unique, and really the crown jewel of Sonic Labs. I would say, let's bring on the man behind it, the brilliant man behind it, so we can get some more information on the technology underlying Sonic, Dr. Bernhard Scholz.
Thank you. Thanks for having me. Today I'm talking about Sonic's technology, and I just want to stress that it took us a long time to develop this technology. It was not just an effort on the technology side, it was also an effort on building a team which is capable of delivering the technology. And it has sort of started with Phantom Opera. It was the predecessor of our Sonic Labs. The Sonic Labs launched at the end of last year, beginning of this year. And when we started 3 years ago, we had sort of a spec sheet, and it read we needed sub-second time to finality. This means a transaction, when a user sends it off, it should be in the ledger in less than a second. We wanted roughly 100 million transactions per day, so that was the volume we wanted to process. And we wanted also very low storage consumption for the nodes running the software of Sonic Labs. We wanted EVM compatibility. We thought this is a big space for DApps. We wanted to have them all on the chain, so EVM compatibility was a big thing for us. And also way back in Phantom days, we had problems with maintaining nodes, so we wanted to have here really easy maintenance. And again, it took us really a long time developing this outstanding technology, and it was not just the technology, it was also building the team. Before I go into block processing today in more detail, especially the database technology, I want to give a brief overview of how the software of a Sonic node works. And you can say there are two major parts of a Sonic client. This is the software running on a Sonic node. One portion is called the block processor, and all these nodes do exactly the same calculation or computations, you can say. And the block processor consists of two parts. It's the virtual machine and the database. And in the past, we experienced big problems with block processing, so we needed really better performance here and being more efficient. We had to really employ a lot of research and technology getting block processing up to speed so that we can really reach the 1 second time to finality and the 100 million transaction per day. So that was really a big challenge for us, and I will talk in a few slides later more about these challenges. The other part is more the distributed system components. A big portion of it is consensus, because all these nodes need to work in sync, and it needs to be fault tolerant and decentralized. So consensus is a big thing here, and we had to develop also a new consensus protocol. But there are also many other parts in the distributed system component, like RPC. So this is really the web interface of these nodes, where clients may process new transactions, or they get queries from DApps asking the value or the balance of a specific account. But other distributed system components also have peer-to-peer functionality, and another big thing is transaction pools. All of these components had to be changed or completely newly written. So it was really a tremendous effort. We are talking about big chunks of code and a lot of person years. The highlight, or really the crown jewels of Sonic Labs technology, the Sonic database. It's really a high-performance native blockchain database. It is in production. We needed 5 different versions, S1 to S5, to really find the optimal for us. And the really good news is that the Sonic database is a native database. So what this means is it really produces data in a binary file rather than using another database like a key value store like LevelDB, BabelDB, and so on for storing the data. And that really makes it efficient because it's a native database. But also we have written a new virtual machine which is fully EVM compatible. Ethereum virtual machines have the problem that they're not very fast, and we needed to use tricks from the programming language research community to really make this fast, and so we do sort of a translation to a more efficient virtual machine on the fly. And finally, which is still sort of work in progress, we are working on a new consensus protocol, which is fundamentally faster because of its incrementalization. But let's talk a little bit more about Sonic database and why is it so fast and so good. And it is always reported in the literature that the database of these nodes are the big issues. So we really need here better technology. And I want to go into a deep dive to really explain why databases are so important and what are the problems with it. And it really starts at the beginning of blockchains, that databases use, the current clients use databases designed for forking chains. And what forking chains do is that their consensus machine is maybe not so advanced, so it may need to allow not a chain, but sort of a chain with side branches. And this is really a weakness of these consensus protocols, which were used very early on or still used. But the problem then is that the database, which stores the balances of accounts, of the nonces, the codes, and the storage for smart contract, need to cope with multiple versions of these states. And they need then also to prune some of these states because some of these side branches will be declared as defunct. And so they work with a data structure called Merkle-Patricia trees. And unfortunately, these data structures are inherently very slow. And we needed to come up with something much better than using, for example, Ethereum's StatesDB or GethMPT, whatever it's called, for our chain. So we really had to rewrite a complete new database for Sonic Labs to make it really fast. Here is a little bit of an explanation why it is slow. The problem is that when you have these blocks coming in and their side branches, then for each block we need to have a state attached. And the state, or world state is called, reflects for this block what is the balance, the accounts, values for this block, and that is very expensive, keeping all these multiple versions, and that causes bloat. So we have very large databases. We are talking about terabytes of data on disk for these larger chains, and it also makes it very slow, and this will affect time to finality, of course, and you may have pending transactions, and you really, as a fast blockchain provider like Sonic Labs, you need to find better ways to overcome this bottleneck. And when we started designing this new database, we had this principal observation that we have a forkless chain. So instead of having side branches like we had in forking chains, Sonic Labs has a better consensus protocol. It's called Lachesis, and in the new form it's called Sonic CS. And this allows that there is only a single evolution of blocks. So we have here full causality, we don't have side branches. And this observation really helped us enormously designing a better database. And we call these databases forkless databases, so we don't need to keep multi-versions of these states in the database. We can start using clever pruning tricks so that we can only keep the last state. We use a native implementation, so we have really binary files storing the information of accounts, and that really makes it very, very fast and powerful. To make it even better, we have two different types of databases in SonicDB. And the idea here is that we have different roles in the network. We have observers and validators, and they don't need to keep the states of all the previous blocks. Only the previous block the state of the previous block is needed. And so we call this database LifeDB, so it really has the state only of the previous block to calculate with the new block the next state. And with that, we can have really efficient data structures to override the previous state and make the calculations which run on top of the database really fast. The other use case is more for historical queries of the database. So when through the RPC interface, queries come along saying, give me the state or the balance of a specific count at block 10, then we need to keep the state of this block 10, but it's really efficiently stored because we know for archive DBs there's only a single sequence of blocks. There's another problem, not just with standard implementations of blockchain databases, not just having this forking issue. There's another problem that they use other databases to store information. So they use which is called key value store databases. And so you have basically two databases, a low-level database and then the blockchain database on top. And this indirection really causes slowdowns. And in literature, this is called a read amplification problem. We have a small blog on our webpage in case you're more interested in these read amplification problems. But what it means is that these information of blockchains is stored in form of trees, so they have small little nodes, and each node needs to be looked up in the database, and each access takes logarithmic time, logarithmic in the number of information items you have in the database, and this is expensive. You would like to have constant time. And this is what we did with Sonic's LifeDB. So when we have these trees storing information, we really use a file-mapped array. And instead of using hashes, which then refer to specific nodes in the blockchain database, we use numbers referring to record numbers in this file-mapped array. And that gives us constant access time for accessing this information. If you want more information about SonicDB, we have some technical reports, we have some blogs, but just to summarize, it's super efficient because we know that we work on a forkless chain, therefore we could design a forkless blockchain database. We specialize this database into two different types of databases, the LiveDB and the ArchiveDB. We have a native implementation, so we don't sit on top of another database. And it's really optimized for disk space and access time, making it super fast in comparison to other competitors. The other part of block processing, and I can't talk too much more, so unfortunately I can't talk more about consensus today, but the other part of block processing is the virtual machine. And here we had to do a lot of innovation as well, but the highest goal, or the highest priority here was to really make the processing EVM compatible. And for this, we developed a very sophisticated testing procedure. Vasudhi will talk maybe tomorrow more about this, but this was really high priority in the design because we wanted that all the dApps which work on Ethereum should also work on our chain. The other problem with virtual machines in that space is that they are inherently very slow, so we needed to really use tricks of the trade to make them fast. And what it really meant is we needed to write a new virtual machine with a different instruction set, and we use dynamic translation. So what it means is before a smart contract is executed, it automatically gets translated to this new virtual machine and then starts executing. There are other problems in the EVM space which really take a lot of time. There's something called the jump test analysis, but what it means is that when you execute a smart contract, an analysis is performed, checking what is code, what is data, and this is unfortunately very slow. Through this new virtual machine translation, we can make this very fast, and caching of crypto hashes is another trick of the trade, which really made the execution of the virtual machine super fast. So this is just an overview diagram how this new virtual machine works. Again, you see this translation via converter, which takes the EVM code to, we call it a long format virtual machine code. It's a much more efficient representation of the Ethereum virtual machine, and that gets then executed on our new virtual machine, making the execution super fast. Here are just a few performance numbers. We have here graphs for the first 10 million blocks. We noticed when we did these experiments that the transaction complexity went quite up from Phantom Opera. We had about 230K gas per transaction in Opera. Now it's much higher. In the first 10 million blocks, it's 350 kilogas. Sonic can, with all these new advances in block processing, based on the virtual machine and the database, we can process now 1,300 megagas per second. The current gas version, which is also highly tuned, which was highly tuned in the last few years, can achieve only 210 megagas. So we are still factors much faster than the Ethereum machine. Here is just a small little trump card. So we have now 48 million blocks. On really good days, we processed up to 1.8 million, which is way below the 100 million. So there's still sort of buffer for processing many more transactions. And we observe blocks up to 2,000 transactions. We always achieve sub-second time to finality, and it's the new way of running these nodes is quite efficient. Before I want to conclude my talk, I want to talk a little bit about our design and implementation philosophy, which is really footed in performance engineering. And so what we do is we have sort of a wheel which we follow religiously. So we start with a prototype, then we do a lot of testing with that prototype till all the functional requirements are fulfilled, like make sure it's EVM compatible, make sure the accounts are found in the database. Then we do a lot of performance evaluation. We do an analysis, seeing what's going on, what needs to be improved, where are the bottlenecks, and then we improve the prototype and the whole process starts again. So this performance engineering idea is really important for us to deliver the performance we see today. Thanks so much. My time is over. Any questions?
Do we have a microphone?
Thank you.